Good afternoon. All right, so let's see. I don't see Jada here. Hopefully she'll come in. But we'll see how that goes here. We're gonna. I'll go ahead and get the lesson set up. So today we're going to work on 10.2, and maybe 10.3. I don't know. Probably just 10.2. We'll see how it goes. Now 10.3 and 10.4 are very short. Okay, so we'll see how that goes. All right, so I guess we'll say Jada is not going to be here. So oh, there she is. Okay. So Weston, thanks for the email. Let me know about Thursday. Tobias, are you going to be here Thursday?
I'm actually not sure. I'll look at my schedule today after school.
Okay, yeah, please let me know. Jada, are you planning on being out at all this week?
Think. Hold on. No, not this week.
Okay. All right. Well, so yeah, Tobias, just let me know, because if we're gonna miss two of you on Thursday, then we'll do something else probably. So anyway, so we'll just see how that goes. So like I said, we're gonna go ahead and start in 10.2. Does anyone have any questions before we get started?
I don't have a question, but I do know I will be done tomorrow because I have a game tomorrow.
You'll be gone tomorrow, but how about Thursday?
Like I said, I don't know about Thursday.
Oh, okay.
I think we have another game. I think it might be Friday.
Okay. So but for sure tomorrow you'll be gone. Thursday Weston will be gone. Okay, so we'll just plan on having regular classes this week. But if something happens where two of you are out, then let me know. Okay, and hopefully I won't be out, because if I'm out, then it kind of messes everything up. So anyway, all right. Well, let's go ahead and get started on the 10.2. Let's see. Let me change the camera. Okay, so this is on infinite series. Now, this section actually is mostly pre-cal. All the big ideas are from Math 189, but it kind of lays the groundwork. Your understanding of infinite series is going to be important for the rest of the chapter. So we just have to make sure that we have the foundation down right. So we'll take as little or more time as we need on this. So if we go, so I'll probably go through it pretty quickly because it is review, but if there's something that we need to go through in more detail, just let me know. Okay. So first, what is an infinite series? Well, a series means you add the terms. The addition is implied. Infinite means that you have an endless number of terms. Now, I know when I was a student, I always thought, well, if you have an infinite number of terms, then they'll add up to infinity, of course. No, that's not the way it works. Okay? And so we'll learn that. Just because you have an infinite number of terms doesn't mean that their sum is always going to be infinite. All right. Okay. So the first infinite series that we really looked at being able to figure out the sum was a geometric series. All right. And so we would have, we had a finite geometric series and infinite geometric series. Okay. And so, so we're actually going to focus on the infinite one, the infinite geometric series. All right, so the sum of an infinite geometric series. So this is the infinite number of mathematicians that walk into the bar problem. So here's the formula. A sub 1 is the first term, R is the common ratio. Now, the idea of a sequence or a sum is important throughout all of mathematics. See, when you actually the integral sign actually means a sum, and the summation sign, the sigma, actually means a sum. So, if we identify our series as a geometric series, then we look at the R, or the common ratio. That is the key to whether or not our sum is going to be a number or if it's going to go to infinity. It's the R that's the deciding factor. Okay? Now, actually, all right, so this is not on your sheet here, but you might remember, what does this series add up to? This is actually the infinite number of mathematicians in a bar. So do you remember how many beers the root beers or whatever that the bartender pours?
He pours 2.
He pours 2. So the idea is that there's an infinite number of things that add up to a specific number. And so the way that we calculate that is with that formula. It's the first term, a sub 1 over 1 minus r. And so when we calculate that, we get 2. And so we get the sum of the series, the sum of these infinite number of things is 2. And so that's a very important idea, that you can add up an infinite number of things and have it get to a specific number. Okay? So, now here's a big idea here. Okay? Is that there's a difference between what does the sequence converge to and what does the series converge to. Okay? So the sequence is what we talked about in 10.1. Okay? We would look at the limit. What were the terms approaching? Okay? So as you look at the terms, see, the terms are getting smaller and smaller and smaller. So the limit was approaching 0. Okay? And so the limit of the terms, the sequence itself, was converging to 0. All right? But the series itself means when you add them all up. So the series adds up to 2. Okay? So they're not the same. So the terms converge to 0, whereas the series, the sum of the terms, converges to 2. So that's a huge difference. The sequence, there we're looking at the limit. Here, all we know so far is a formula, okay, that we learned, the a sub 1 over 1 minus r. Okay? Now let's go back. All right. So, is something like this geometric? How can you tell? Is there a number that's multiplied by each time? As n goes up, what do you multiply by, if anything? What do you think?
Can you say the question a little differently?
Okay, so this is practice 1 from your sheet.
Mm-hmm.
Okay, I want to know, is this series here a geometric series? So to be geometric, it has to have an r value that you're multiplying by each time. So what do you think?
Yes, it is geometric.
So it is geometric because, see, the 1/9 doesn't change as n goes up. But as n goes up, what are you multiplying by each time?
The 1/3?
The 1/3. See here, when n is 1, then this term goes away. So you just have 1/9. But then when n is 2, then you're multiplying by 1/3. And then when n is 3, it's 1/3 times 1/3. And so from there on, as n goes up, you're multiplying by another 1/3. So that's r. So is this series geometric? Yes. And the r is 1/3. Okay? All right, any questions on that? Okay, so now if okay, so whenever you have a geometric series, okay, so it's kind of written like this when it's in summation form, or this is the formula that we use in pre-cal. If it converges, if the r is between -1 and 1. So sometimes you'll see that written like that. Sometimes you'll see it written like this. The absolute value of r is less than 1. So if that happens, then the series, the sum of all the terms, converges. Okay? Now, if the r is greater than, or if the absolute value of r is greater than or equal to 1, the series diverges. So this is the first test, okay, of many that we will learn in chapter 10 to learn if a series diverges. Is you check, is it a geometric series? Well, what's r? And that's going to be the first test that we use. Okay? So, like with this one, to tell if this series converges or diverges, you say, oh, this is a geometric series. The r that's being multiplied by each time is 1/3. Since r is between -1 and 1, the series converges. And then we can calculate what it converges to. Okay? All right. So now let's look at this one. For this series, what are the first 3 terms? So you look at the index and you say, okay, we're going to start with 0. So when n is 0 here and here, this will go to 1, this will go to 1. So you just get 5. Okay, then when n is 1, then -1 to the first times 5 over 4 to the first, well, that's -5/4. But then when n is 2, -1 squared is 1, 4 squared is 16, so that's going to give me 5/16. So now, next we use this word, this term partial sum. So even though this goes to infinity, a partial sum is where we're adding a certain number of terms. So like the 5th partial sum would be add up the first 5 terms. So here we're asked to find the 3rd partial sum. So that just means to add up the first 3 terms. So that's, you could put that in the calculator, or we could get a common denominator and add. Either way, it's fine. Okay? Now, is this a geometric series? Well, each time as n goes up, we're multiplying by another -1 on top and a 4 on the bottom. So that, yes, it is a geometric series. Okay, and the first term we said was 5, and the r was -1/4. So does the series converge? Well, since this is between -1 and 1, the answer is yes, it converges. Now, if we need to know what it converges to, then we use this formula. A sub 1, which was 5, over 1 minus r, which is -1/4. So that's 5 over 5/4, which you flip the fraction and multiply. And so the answer is 4. So the series converges to 4. All right? So that's the sum of all the terms would be 4. All right? So go ahead and try practice 1.5. All right, so Weston, what are the first 3 terms?
5/4, -5/4, and 5/4.
Okay, good. All right, Tobias, what's the third partial sum?
5/4.
Okay, good. All right, Jada, is this a geometric series?
Yeah.
So what is a sub 1?
Oh, hold on. I didn't get that far yet.
Okay.
Would you use the s the?
No. The a sub 1 just means the first term. So it's just the first term we got 5/4.
Yeah, 5/4.
Okay. And what is r?
-1.
-1. All right, so Weston, does the series converge or diverge?
It converges to 0.
Nope.
Nope.
So what's r again?
-1.
Okay, now look at your rule that you wrote down for part 2.
Oh, okay. Then it is not.
See, it's not between.
Yeah. Okay.
So if it's right on the line, if it's right at 1, there's no or equal to there. So if r equals 1 or -1, it diverges. Okay? All right? Any questions? Okay. All right. So now let's look at this one. I want you to see if you can figure out, does this converge or diverge? And then I want you to tell me, if it converges, tell me what it converges to. All right, so Tobias, does this converge or diverge?
I got that it converges to 1/6.
Converges to 1/6. I believe that is correct. Converges to 1/6. There's kind of the work there. All right, good. Excellent. Any questions on that? Okay. Okay, applications of geometric series. We can use a geometric series to calculate the total distance traveled by a bouncing ball if the height of each rebound is reduced by a common ratio. So like, let's say if you have a super ball and you bounce it and each bounce is only 2/3 of the previous bounce. Well, then that's a geometric series. And so you can calculate the total distance. We actually did this problem. If you had me for trig, we did this problem, okay? Where you say, all right, so let's say if the ball goes down and then it rebounds up to the height of A times R. So here's A, so maybe R is 2/3, so it's 2/3 this height. Well, then it's R squared, and then R cubed, and so on. So if you're just trying to calculate the distance up or the distance down, then you can just add up those values. Okay? So, so the distance the ball travels upward, so this first upward trajectory, the height is A times R. And then A times R squared, and then A times R to the third, and so forth. So how would you write that as a geometric? How would you write that as a geometric series? Jada, what do you think? How would you write the sum of all? Let's see, all the in practice 3 it says find the distance the ball travels upward. So how would you write that as a geometric series?
I don't know.
Okay, so see this distance upward is just A times R, AR. And then this upward would be AR squared, and then AR cubed, and so on. So how do we write that? Well, it's the summation. See, we're adding all these up. The summation of, as n goes from 1 to infinity, of AR to the n. So it's AR to the first, AR to the second, AR to the third, and then we're adding those up. And so that would be the summation. Okay? All right. Okay. All right, next. Repeating decimals. You do this like in Algebra 1, where you write repeating decimals as fractions. Okay? Well, we can use infinite series to write repeating decimals as fractions. This is kind of another way to do it. All right? Is you say, okay, so, okay, the non-repeating part is 5. So you just kind of have that to the side. All right? And then you'll say, okay, then the next part is 2, 3, and then 0.0023, and 0.00023, and so on. This is the infinite series part. All right? So you just would keep the 5 alone, and then you say, all right, well, my first term here, so this is my infinite series part. The first term here is 0.23. And then to go from here to the next, see, if you repeat if you're repeating one decimal, the R is just 0.1. If you're repeating 2 decimals, it's 0.01. 3 decimals, 0.001, and so forth. That's the R. So to calculate this sum, then it's just going to be the first term over 1 minus R, or 5 plus 23/99. Now, 5 and 23/99, that's a perfectly good mixed number, but it just says do the ratio of 2 integers. So then you would write this as an improper fraction, 5 times 99 plus 23, and so you get 518/99. All right, so see if you can do practice 4. Which is a little bit easier than this one. All right, so Weston, what'd you get?
25/9.
25/9 is correct. Okay, so here you kind of break off the 2, and then you think of the first term in your infinite series here is 0.7. And then the R in this one is just 0.1 because you're just multiplying by 1/10 to get to the next term. And so then when you do 0.7 over 1 minus 0.1, so you get 2 7/9 or 25/9. Okay. All right, any questions on that? Okay. All right, next. Telescoping series. Now, remember when we did partial fraction decomposition? This is kind of showing you how this breaks down. Remember, before we would have to find the A and the B. So this is telling you that, hey, when you break this down, the A is 1 and the B is -1. So this breaks down as 1 over n plus -1 over n plus 1. All right, so why am I showing you that? Well, because, see, if I want to know what's the sum of this series, does it converge? You know, what's the deal here? It helps, instead of looking at this, it helps if I break it down using the partial fraction decomposition. How does that help? Well, watch what happens when I start plugging in numbers, starting with 1. So when I plug in 1, then I get 1 over 1, which is 1, plus -1 over 2, or -1/2. All right, then when n is 2, I get 1/2 plus -1 over 2 plus 1, or -1/3. Then when n is 3, I get plus 1/3 minus 1/4, and so on. So what's cool about that is the second term of this always cancels with the first term of the next number. And so everything after the 1 is going to cancel. And so this series converges to 1. All right, so in your practice problem, it says, what about if I multiply this series by a 3 out front? The rest of it is still the same. So what does logic tell you that this should add up to?
3.
3. Exactly. So we actually had a formula for that last time where we said if we have a constant times a series, it's just the sum is the constant times the series. So this 3, if this whole series converges to 1 and I multiply it by a number in front, then it's just going to converge to 3 times 1, or 3. Okay. All right. Now, this says if the sum of the terms converge, then the terms themselves approach 0. Now, this doesn't mean that if the terms approach 0, then the sum converges. You got to be careful that you don't make the what we call the converse error here. You can't flip the if and the then. So if the series converges, then the terms themselves converge to 0. Okay? So then let's look at this. Does this series, what do you think about this series? Would this converge or diverge?
Diverge.
Why do you say that?
Because the rate is -1. The R is -1.
Okay. So here, so this diverges. So you can think of this as the R is -1. So you could think of this as a geometric series. But, and see what I'm saying, see, even though this bounces back and forth, see, if it doesn't approach a certain number, then the series itself, if it were to converge, see, you just say for a second, suppose the series converges, then the a sub n's approach 0. Well, here the a sub n's don't approach 0, so it's got to diverge. Okay, I kind of like how you were thinking of this too, as a geometric series, because it is. All right, now, so we've talked about a geometric series. All right, now this is the next test. This is called the nth term test for divergence. Now, the limitation, I mean, this is a really good test, but it only tests to see if it diverges. You can't ever say the series converges based on this. So that's why it's called the test for divergence. Now, I kind of don't like how the other tests, they write if this, then this. And then all of a sudden this one, they kind of write backwards. So I like it like this. Like if the limit of the a sub n's if the limit does not exist or is not equal to 0, then the series diverges. So I always like the if part first. But that's how the book writes it. So if the limit of the series as n approaches infinity equals 0, we know nothing. Okay, from this test. So when you do this, you actually hope that you get anything except 0. Because if you get anything except 0, the answer is diverges. But if you get 0 from this test, then you don't know. Okay? So it could. It could. Okay? All right. So you think, okay, what's the limit of this as n approaches infinity? Well, that would be infinity squared or infinity. So we would say the limit is infinity or does not exist. And so therefore the series diverges. Okay? Or with this one. If we look at the limit of this, remember when it limits at infinity, the easiest way to do those is to compare the powers. If the power is the same, then it's A over B, the ratio of the leading coefficients. So 1 over 1 is 1. So what does that mean if we get 1, according to this test? Then if we get anything other than 0, the answer is it diverges. Okay? So if we get does not exist or infinity, if we get a number, then it diverges. When you take the limit as n approaches infinity. But if you get 0, then you got nothing. Okay? Then you have to do something else. Okay? So see if you can go ahead and do practice 7. All right, Tobias, what do you think?
Does it diverge?
It diverges. What did you get for the limit?
I got negative infinity over infinity.
Okay, now when you get in negative infinity over infinity, that's an indeterminate form. So you can't stop there. Okay, so you either have to use L'Hopital's rule or do what I said there in the last one where you compare the powers. And if the powers here on the ends are the same, then it's the ratio of the leading coefficient. So it would be negative 1/2. So, and since we got a number other than 0, then it diverges. Okay? But you can't stop at infinity over infinity or infinity to the 0 or 0 to the infinity or any of those indeterminate forms. Okay? All right, next, grouping clusters. If the terms of a sequence can be grouped into infinitely many clusters, each of which add to 1, then the partial sums increase without bound and the series diverges to infinity. So if we have one group of 1 that adds up to 1, the next adds up to 1, then eventually it's going to go to infinity. Okay? So the example here is, see this, how this, here we have 1, and then the next two numbers add up to 1, And then the next 4 numbers add up to 1, and so on. And so you can say, well, 1 plus 1 plus 1, eventually it's going to go to infinity. So this diverges. So if you can find any clusters of 1s, okay? So see if you can find that in practice 8. All right, so do you see the clusters that add up to 1? So then this would diverge. Okay, it's just a matter of seeing it. All right, any questions on that? So sometimes if you're stuck, you actually can write out the terms and see if you see a pattern like that. Okay, now, so these rules, don't write these up here. I've kind of combined them into 2. All right, so these are the 2 that I want you to write down. So if a summation, if a series diverges, then anytime, this is what we were talking about before, if you multiply by a constant, then that's also going to make it diverge. So if the series goes to infinity, if you have 5 times that, it's still going to go to infinity and diverge. And then the second one says, if you're adding a series that converges with a series that diverges, if you add or subtract those together, it's going to diverge. Because if you have infinity or negative infinity and you add a constant or subtract a constant, it's still going to go to infinity or negative infinity. Okay. All right. So here, like if we have 4 over 2 to the n, see, it might be easier to pull the 4 out front because it's just a constant. And then just focus on 1 over 2 to the n. Okay? So this part right here, is this geometric? 1 over 2 to the n? Yes. What are you multiplying by each time? See, if you looked at the numbers here, you'd be 2 to the 0 is 1, so you'd have 1, and then 1/2, and then 1/4. So what are you multiplying by each time?
1/2.
1/2. Okay? This is the infinite mathematicians again. So what is this going to add up to? The 1 over 2 to the n.
2.
So that adds up to 2. So then you just multiply that by the 4 and get 8. So it's just going to, so pulling that constant out, whenever you have a constant on top, it's just easier to just pull that out front and then deal with the rest of it. Okay? All right. So the last thing on this sheet is about reindexing. It says we can add a finite number of terms to a series or delete a finite number of terms without altering the series convergence or divergence. Okay, let's see. Oh, no. We can reindex any series. Oh, this is, I've changed the thing. Actually, this part. So this part that's in red. If you change the index, that's like you're adding a term, or anyway, you're not going to change the convergence or divergence if you alter the the index. Okay? So it doesn't change the sequence. So like here, if I want my a sub n's to go from 0 to 5 or from 1 to 6, and I have the same formula here, these will be the same. So that part doesn't matter. Now, if I have a formula, though, I might have to alter that. Okay? So let's look at this. This says rewrite the series as a sum beginning with n equals 0. Okay? Now, this is going to be a little tough. But think about it. What would the first term be in this? If I plugged in 1 for n, what would I get? 5 over
2.
Yeah, so I get 5 over 2. So 5 over, and then I get 1 times 1 plus 1. All right, now, if I change the index to start at 0, how could I change the formula so it would give me the same thing? Let's see. So if I started at 0, so if I had n go from 0 to infinity, I would still have the 5, but what would I change these to? Anybody? So if n is 0, how could I get it to be a 1 here? I could change.
Can you square
Go
it?
ahead.
Can you square it?
Well, no, because it would be 0 squared, so it'd still be 0. So to make if I plugged in 0 for n, to make it equal to 1, just change the formula from n here to n plus 1. Okay? Now, I want this to be 2. So I need to change this from n plus 1 to n plus 2. Okay? So this is just saying that, look, if you change the index, that's okay, but you're going to have to change the formula a little bit so that it doesn't change the answer. Okay? All right, well, that's it for that section. So a little bit of practice would probably